Yo, hello, video game nerd people. The long-awaited regression video. I'm just making sure I got everything set up, and I do. Remember, my goal is to not say, okay, but I will fail. Just a little review. I'm going to walk you through the R code that we generated to sort of make a simple test of our hypothesis that dominance is under selection when you play Darwin's demons. And we tested that hypothesis by setting up an experiment where I played the game 3 times, where two of the fitness functions were turned on, and 3 times where the fitness functions were all turned off. And our hypothesis predicts that when the fitness functions are turned off, dominance should not evolve, but when the fitness functions are turned on, and they can actually reproduce by natural selection, dominance should evolve and be significantly different at the end of the experiment from the control. So I have 6 replicates that we've been working with this whole time, and this is the R code that we've been using, and I'll just kind of walk everybody through it. We'll set our working directory, load up the libraries that we like to use, and create our empty data frame where we will put the stuff. And then, using this little loop, we'll look in our working directory. We will find all the CSV files, read them in one at a time, add some metadata, and add them all, pile them all up into one big data file called all the data, and off we go. And now that is done. These are the kinds of things that would be really, really difficult to do in Excel. Now, this little line, I can't remember if I've explained this before. What I'm doing here is for a couple of the experiments, I kind of got caught up with playing the game, and my goal was to have 18 replicates, or 18 generations in each replicate. And for a couple of them, I played longer. I played to like 19 or 20 generations, and I just want to clean up the data and say, look, I'm going to only go to 18 generations for each replicate, so everything's the same. So if I do that, I just subset all the data, and I just take out everything, or I keep everything where a generation is less than 19. Now, what we did up till now was we were just really looking at the average dominance that was produced at the end of the experiment for each of our 2 treatment groups. So I'm going to recreate that, and then I'll tell you why that's really not a very powerful analysis, and it leaves a lot of data on the table. So first thing we do here is we're going to use this code to calculate the averages for each replicate, each generation, and each treatment for this trait dominance. And so we do that, and now I've got a bunch of averages in a data file. So this is called averages here, and now it's created this thing called averages, and now it's just like, here's this data file, generation 0 through 18. It is from the control group for our variable called selection. And this is the average dominance of the aliens per generation. And then this is the next data file, and so forth. Again, these are the kinds of operations that R excels at, and Excel makes it difficult when you're working with multiple data files. And then what we want to do is visualize our data. So what we're going to do is we're going to take all the data, we're just going to make a plot of dominance against generation. We'll color it by our treatment variable selection. And we'll make a scatter plot so that each alien in our experiment is represented by one data point. And we're also going to use the averages to plot as a line in black here, the average value for each generation in each file. And we just want to look at this facet wrap file command just makes a separate graph for every file in our experiment. This, as you run experiments with more and more and more data files, this becomes less and less useful because the graphs become super small. But anyway, if we do that, this should look somewhat familiar. We've got, and this is not ideal, it's named by the file name, which isn't really, I mean, it's not informative, and it's getting truncated here. I'll zoom in so you can see it a bit better. So here are different file names. Red dots are the control condition, and whatever, light blue, whatever that color is, dots are the evolution is on, fitness functions are on condition. And just by eye, you can see that when evolution is on, it sure does seem like dominance is trending downwards, where it is relatively flat when under control conditions. But could that have happened by chance? We don't know. When we say it kind of looks like it's trending down, we're scientists, that's insufficient. We have to do a statistical test. We have to be able to articulate the confidence with which we think the data support or refute our hypothesis. And so what we did there is we just said, hey, let's just use generation 18. The very end of the experiment, we're going to calculate the averages of our groups in generation 18, and so we've done that here. And then we're just going to do a simple t-test and using the linear model command, and we're just going to ask, hey, are these averages different? And we did that, and it turned out to be significant. And then what we're going to do is just use this code to graph that out. And so I'll show you the graph, and then we'll... Okay. And so what we had here is we calculated this out, and on average, the average dominance ended up at generation 18 under control conditions around 0. And these are our error bars, plus or minus the standard error. The average dominance when evolution was turned on, the E condition, ended up right around -9, and this is the standard error. And then if you just get the summary of this object that has our analysis in it, what this says is our intercept is the sort of grand average across the entire experiment, and this says this group selection E, its average is -9.25, and the p-value, the probability of observing this difference, is 0.02, which means the probability if we ran this experiment 100 times and the difference wasn't actually there, we would observe a difference this big 2% of the time. And that's below what we usually accept as a p-value for these simple kinds of experiments of 0.05. And so we would say these data are consistent with our hypothesis. And that's sufficient for your first run. And so this is, I'm just checking how long I've been talking now. So that's 8 minutes of review. Oof, we'll see if I can tighten that up in post. I'm trying to keep the videos short and punchy, but it's difficult. What I want to show you now is the problem, how to solve the problem of leaving all of the data. We just threw out 90% of our data, 95% of our data. We ran this experiment for 18 generations, and we took 17 generations worth of data and threw it away. Not ideal, right? So let's look at a different statistical analysis we can do that uses more of the data that we collected. And so what we're going to do is we're going to build off of this plot that I showed you how to make. And so this plot here, we're going to use the data that we calculated, the means for each file across generation, the mean of dominance, and we color it by our treatment type, and we group it by file. And so, and what I've done is I've added a geom smooth command here, and the method is linear model. So that's just y equals x kind of thing. And we, make sure we do it so that it knows there's two groups. And what this does is it makes essentially a very simple regression graph. And so the lighter weight lines are the averages of dominance for each file, and they're colored by their treatment group. So these are the ones where selection is turned on and selection is turned off. And then the thick line with the gray around it is that geom smooth command. It's essentially saying, what's the linear regression line of best fit for those data? And what it shows is that's more or less flat here for the control condition, and the gray area is essentially the 95% confidence interval of that regression line. And then the blue line here, the thick blue line with the gray, shows that when evolution is turned on, dominance tends to go down. Okay. And now I want to show you the statistical commands we can do to kind of quantify this effect and get a p-value out of this, because this shows some statistical information, but it doesn't give you the p-value. What we're really interested in here is, are those slopes significantly different? Does the effect of the effect on mean dominance, the rate of change of mean dominance, differ between control and evolution is on conditions? Because if it does, if that is significantly different, if those rates of change are significantly different, that is a result that supports our hypothesis that dominance is under selection. So we're going to do a little statistical analysis. We're going to do a little regression test, and we're going to estimate this slope, and we're going to estimate this slope, and we're going to test to see if they're significantly different. There's several different ways you can do this, and almost certainly, as I show you how to do this, if you took my video and you ran off to your Stats 250 professor or Stats 401 professor or some statistician, almost certainly they would be like, he got it kind of right, but regression can get really complicated really quickly, and there's actually a bunch of stuff that I'm not going to show you because it's not a statistics class about testing the assumptions of regression and all of that kind of stuff. But this will be sufficient for a genetics class. So off we go. And I've got another set of code over here. You'll see me looking away periodically because I've got another set of code that I have tested and I know works. First thing I want to do is, you can see with this plot, we've got two regression lines, one for each treatment group. And let's just estimate those slopes. So we'll just take the data apart and we'll estimate the red slope and the blue slope, so to speak. And there's lots of different ways to do this. I'm going to do it in a way that your statistics professors would crucify me for, but it's a way that sort of slowly walks you through the logic of what's going on. Let's first estimate the slope of the control condition. And so what I'm going to do is I'm going to go and I'm just going to subset the data that we're using, the averages, and I'm going to make a new data frame called cont average, control averages. And I'm only going to use our control condition. And remember, when we're subsetting data with this subset command, we want to say this is the variable selection. So I'll go and I'll show you averages, right? Averages has this variable called selection, and one of the values is C. And if I want to say, hey, only use the stuff where the value of that variable is C, remember you have to use two equal signs. I actually screwed this up earlier today when I was testing it. So we'll run that, and we've got a new data frame. And it is half the size of the other data frame because we're only using half the data, just the stuff where the value for selection is C. And it's still every file, generation 1 through 18, mean dominance. And now what I'm going to do is I'm just going to do a simple linear regression using just that data file. So I'm going to make an object called conreg, which is the results of this linear model test. I'm going to use the data called cont average that we just created. The formula I'm using is mean dominance is a function of generation. And when I do that, I create this thing called conreg, but I don't want you to click on it. Let's just have a look at the summary of that down here in our console window. And I'm just going to make this just a bit bigger here so that you can see. And so summary conreg, so this tells you what the call was. That's fine. It's good for troubleshooting because it's a genetics class, not a statistics class. So don't worry about the residuals. What I'm interested in is this coefficients thing. Okay. And so the intercept, we're interested in three things here. The intercept, it's not really that interesting. The slope, and then the p-value associated with the slope, which tests whether it is significantly different from 0. So intercept, the intercept of the model, if you go over here, it says, hey, this line crosses the 0 line for generation at a value of negative 0.4. Right? I mean, you can visually confirm that that's correct. It's really not that useful for us. We're interested in the slope. And this says the slope of mean dominance as a function of generation is 0.02. So it says mean dominance tends to go up by a value of 0.02 per generation on average. And this p-value is 0.23. That means that if we did this experiment 100 times and there no real difference, no real relationship existed, we would observe a slope like that 23% of the time. This p-value is not below 0.05. And what it says is this slope is not significantly different from 0. And just intuitively, if you go look at this, the red lines, that's the analysis we're doing, it's pretty much flat. Right? The standard errors include 0 at both ends. Dominance is not changing. We've estimated the slope to be not significantly different from 0 under the control conditions. Now, let's do the same thing under the conditions where evolution, the fitness functions are turned on. Our hypothesis predicts that the slope will be significantly different from 0. So I'm going to do another set of lines. And this time I'm going to create a new object called cellreg, and that first, let's get the data we need. So first, I'm going to do a data frame called cell average or whatever, cell average, SELAVG. And in that, I want to put the subset of our averages where selection has the value capital E. And so when I run that, I've got a new thing called cell average, and again, it's all of the E data, the mean dominance. And then I'm going to run a linear model using those data, and I'm going to say, hey, test whether the relationship between mean dominance and generation is the slope is significantly different from 0. So we'll run that, and then we'll summarize that. And now we're looking at this blue line over here. Just gonna give myself some space, and I'll post this code again. And so now, again, we don't really care about this stuff all that much. What we're interested in is the coefficients. And so let's ignore the intercepts for right now. This says the blue line crosses the 0 line at the x equals 0 at a value of 0.89. But what we estimate is every generation, on average, when the fitness functions are turned on, mean dominance is reduced by 0.498, essentially 0.5. Negative 0.5 is our slope. And if you look over here, this p-value is 6.88 times 10 to the minus 14. So that p-value is effectively 0. And what these stars mean is less than 0.001, 2 stars means less than 0.01, 1 star equals less than 0.05, and so forth. This p-value is really, really low. What that means in layperson terms is observing this kind of relationship when one doesn't actually exist, if we repeated this experiment hundreds of times, the probability of observing that relationship by chance is 6.88 times 10 to the minus 14. It's effectively 0. So this slope, this relationship between dominance and over time, is highly significant, and that is consistent with our hypothesis This slope is negative 0.5. This slope is 0. Last thing I'm going to show you is, so again, that's sufficient. That's consistent with our hypothesis. The last thing I want to show you, though, is how to test whether those two slopes are significantly different. Which is, we kind of did that already, but we haven't really. And so the last thing I want to show you, and this is about as complicated as I want to get in this class for statistical analysis, is how to do this analysis where we don't split it out by control and selection equals E, and we use the entire data set. And you're going to get the same answer. The numbers will vary a little bit because you're using the entire data set, but it's actually less clumsy in my opinion. So in this case, we're going to create an object called reg dom averages. I'm bad at naming things, okay? And we're going to do a linear model of the whole data set, averages, that contains both the C and E treatment groups. And our formula is mean dominance is a function, and in this case, I put generation colon selection. This is the first thing that we can do. So if we run that and then summarize it, this should look familiar. Okay, this estimates separately for each group the coefficients of the slope, and you can see the estimates are slightly different because we're using the entire data. So the model that has the same intercept and so forth, and so, but you get the same answer. The relationship between in the control group between dominance and generation is not significantly different from 0. The relationship in the evolution on group, the E group, is significantly different from 0 and approximately negative 0.5. All right. The last thing, and again, you know, if you understand this and you feel like you're learning something and you want to use these types of analyses in your projects, awesome. If you'd rather reduce it down and just do the simple t-test analyses for these kinds of projects, also fine. Just in your discussion, acknowledge that with the t-test analysis, your experimental power might be reduced because you're throwing away a lot of data. So just justify which analysis you chose. And it's okay to use the one you understand for right now. That might be less powerful as you're learning how to do this. It's better to be doing something you understand and sort of proceeding with that than I ran some code, I don't really understand what it's doing, but the magic p-value is less than 0.05, so yay. That's not okay. Anyway, I hope that was helpful. I'll go ahead and clean this up and throw it up on YouTube, and then I think I might send out an email. I don't know what else everybody wants me to cover. There's lots of other kinds of experiments that we can do. We can estimate heritabilities, we can estimate effective population sizes, we can do different experiments testing where different players or different ships cause different patterns of evolution and other traits. I'm open to helping people do whatever they want. I can make a video on the experiment that you want to do, and we can kind of work through it together. But you know, not a ton of views on these videos. I know Sam and Avery and a few other people are plowing ahead, and that's awesome. But I don't really want to forge ahead with stuff that nobody ultimately wants to use. So looking for feedback at this point. Hope everybody's doing well in the global apocalypse. I'm going to sign off.